talk in this session is our formal verification. It's Tobias Ludwig from LUBIS EDA, where he's the CEO. He's worked in formal verification since 2014. He acquired a PhD from TU Kaiserslautern in the area of formal verification. In 2020, he founded LUBIS EDA as CEO with the goal of to do more formal verification to the market. Thank you.
Thank you very much.
Yeah, it should be.
All right. Good. All right. That sounds better.
Sorry to begin.
Yeah, I'm quite excited. The slides are brand new. Mike was sending me an email. Tobias, we need those slides, but the team just got ready and I wanted to show the real results in the end. So I had to wait until yesterday evening. Another talk about formal. We had two great talks already in the morning. This time we have a little bit of a different goal. Our company's goal is to make formal as easy as possible. We are mainly a service provider for formal verification. We also do trainings, but I'm not going to talk about this today. You guys are here for our software that can help you doing formal verification more easily. Our team is pretty strong right now. We're located in Germany, and actually anything related to formal is interesting to us. This is our typical flow if we want to do a formal project. I just want to point out that whatever I talk about today, there are some steps that you cannot hump over, even if you would use a software like we do. So you have to do the planning and you have to do the sign-off. But today, we're going to focus on how can we execute a property verification and how can we verify things. And for this, I developed a software many, many years ago when I was still doing my PhD that uses an abstract model in order to generate assertions that we then can use on the proof. And the good thing about the abstract model is it is also executable. And I will first introduce today a small dumbed down example, and then I will talk about a real world project which we just finished. That's a SHA-512 core that we verified by using a software like this. So the overall idea for today is that we start with an abstract model. It's a C++ code in our case. We feed it into our tool and we generate all the assertions that you need from that model. I will explain how we do that and why it is a sound thing to do. Then you load the generated assertions together with your RTL in a formal tool. It's plain SVA, so in theory you can use any formal tool of your choice, and then you run the assertions. And when everything passes, you know that whatever you described in the model is exactly what the designer is doing. If you have a bug, of course, as Nick said this morning, maybe you need to update your model, maybe you forgot about something, or it is a real bug in the design. That's of course then up to the debugging process. Now, our tool basically reads in a model and it has two phases. Internally, we fully parse the model and then we apply our secret sauce. That's symbolic optimizations, lots of algorithms, and lots of years of debugging. And then in the end, we throw out an assertion IP that is easy to read, that clearly document what the algorithm is doing, and the properties are generated such that they form a complete set of properties. What does that mean? Completeness is a mathematical definition and it shows that a set of property fully covers the design intent. Yeah? So there's no gaps in the proof once all properties sold. If you have a failing assertion, you don't have any news, but if all properties sold, then we know whatever we specified in the model is also correctly implemented in the design. How does it work? This is a very simple example, but when we do implement abstract models, the key thing is to identify the very, very conceptual abstract states of the RTL design. That's the task of a formal engineer anyways. We have to figure out what is the abstract behavior of the block. Ideally, we have a spec that formalizes that, but as already mentioned this morning, oftentimes we do not get this formalized spec that really clearly defines what is the abstract behavior of the design. So what we do is we formulate in this code what we think is the abstract behavior of the block. And we want to focus on the communication states of the design. And in this example here, we have two communication states where we read a new message from a bus, could be an XC bus or I2C or whatever you have. And once the handshake happens, then we know that then the design starts operating. And depending on the mode that we receive on the request, we, for example, start encoding some data. And once that is done, we want to write back the data on the bus. It's a very simple model. You can simulate it easily. You can even look at it. It's no problem. What our tool does, it reads in such a description, and in the first step, extracts the abstract state machine from such a description. And we can see that from the state bus in read, if we just follow the code, we can go to out. Here we may need to wait in the simulation until the data is received on the output side. That's indicated by this arrow here. But then from the wait block back, we come back here because this is a while true loop. Yeah? There's many different ways you can implement it. We're choosing this one here, but also there's another path. Yeah. So if we read in a message where the mode is not equal to send, then of course we just jump over all this code and go back to the next message. There's this wait loop here, but for the sake of demonstration, we focus on the encoding instruction. So we get a new message, we want to encode it and send it back. Could be ECC check or some kind of hashing or whatever you want to imagine. And for each of those transitions in the abstract state machine, we will now generate an assertion for you. And this is pseudocode, but it's easy to read, so I stick with this one for now. And basically, all assertions kind of look like this. We assume a certain start state, then we have our trigger condition, and that is that the mode is equal to send. And then the assertion generates the desired end state and the desired output. It looks simple now, but it can get more complex, as you can see later in the example. And we have such an assertion for each transition in the state machine. And when all properties hold, then we know that whatever is specified in the abstract model is also implemented correctly in the RTL design. Well, behavioral synthesis and properties is a new thing. So what makes us special is that, first of all, we abstract from the timing, right? So this encoding operation could be implemented as one huge combinational blob, and it's done in one clock tick, fine, or even combinationally. But it could also take millions of clock cycles, right? We don't know. So one part that we have to do is we have to specify, well, what's actually our desired output timing? Yeah? And then the second thing, I will get to that later, the symbols that we have here could also be more complex than just having a parallel 32-bit wide input port. Could be coming in chunks or different various of formats. I will go to that later. Now, where does the abstraction come in? As I said already, the simple encode instruction, which is just one assertion, and that's where actually formal gets interesting, where we get the abstraction, could take multiple hundreds or thousands of RTL clock cycles. So if you look at that path here, we already see that in order to transition from receiving a message in the RTL design, it takes at least 2 clock ticks before we end up in the right state. And that can become arbitrarily complex depending on what you choose on how to implement your data path. Practically, the properties look like this. This is now a pretty normal SVA, which some people can read, some people not. So I will just go over some details of that code. And yeah, on top here, we have a parameter for length. We have like a whole set of boilerplate and load scripts where you can specify those parameters. And yeah, we want to store some data at the beginning of the command, and that we do with this one here. So once we receive the data, we want to store it in this local variable here. Then we assume a certain start state R. And again, many RTL designs do not explicitly implement a state machine. That's the task of the formal engineer to figure out when which registers are set, what formulates this abstract state read. That's not always explicitly given, so the designer has to figure this out. And we also have to trigger that the mode is equal to send, and then we want to prove that at the end of the operation, we see the correct output. Now, that looks very simple, but there's a caveat to it. The data that we want to see, let's say it's a 32-bit wide data. In real life, we don't always see, for example, a 32-bit wide port. If we see, telling what the data is really easy. It's just the input port. But what happens if this data comes in sequentially within 4 clock ticks with 8 bits per beat? Well, then we need to specify that also. Yeah? We need to know how our data package is composed over time. And this is what we call refinement. And this is what we always need to do on the primary IOs to specify what format does the data has when it comes in, what's the timing of that, and also for the outputs, what's the intended output behavior. So even though we have automated many things, this is the last manual step, but there's hope. I will get that to the end. I will get to that in the end. Sounds like a lot of hassle, right? Writing the model, generating the assertions, doing the refinement, proving it, getting failing assertions, debug it. But I think there's 3 good reasons why you should still maybe think about using a flow like this. First of all, it's much easier to generate the properties from the abstract model than write them by hand. Yeah. It's very error prone and it's very time consuming. In the example I will show here, we generated over 900 lines of code from about 80 lines of C++ code. Yeah. And then if you write those 900 lines by hand, I bet you make a mistake. Yeah. And who is reviewing all that? Then second, if you don't already have it, you finally have a formalized spec that clearly defines what the design should do. And lastly, that's a benefit of having a tool like ours is that you can split up the properties in many, many, many small properties. So if you write stuff by hand, which we still do in the service projects, you rather have like one property that proves a lot than 100 small properties just prove something specific, because writing 100 properties is time consuming and error prone. But if you have a tool, you can just let the tool split everything apart. And if you have 1 million properties and one fails, you only have to focus on this one thing, yeah? Assuming that you have enough licenses to run all of them in parallel, of course. Now, the example that we get to is from the Calypso project. I'm not sure if anyone knows. It's the new hardware root of trust. It's a joint project, I think, of Google, Microsoft, and AMD, and some other companies are joining as well. And as part of this project, they also implement some hashing algorithms like SHA-512 and other ones, ECC, HAMAC, and so on. And we were asked to verify one of these blocks. It's not public yet, but once it's signed off, you can follow us on LinkedIn. We will publish it so you can have a look yourself on the Calypso project. It will be published there, the code. Now, if you're not familiar with SHA, it's not a problem. It's a very simple algorithm from the theory. We have different rounds, and each round we shuffle some input data, and in the end, we get a digest out. One round of this SHA feeds in 1K bits, and we get 512 bits out. And you do that as many blocks as you have. So if your message is, I don't know, 4K wide, you need 4 iterations of this overall algorithm. After each iteration, your digest will update. And anytime we have something like this, we can use our approach to model this. And what you see here is the real world code. And what you can do in our tool, but you don't have to, is explicitly express states. But if you leave them out, the tool will place them automatically where they need to be. And once you've done that, then in the next step, we can start focusing on generating the assertions. And this time, I'm going to focus on a single SHA round, because I think that's the most interesting stuff to look at, because after that, after we've computed the digest, then we just do some bit slicing depending on the mode. That's not that interesting, but the SHA round itself is very interesting. And to be clear, we have a test vector with more than 100,000 entries from the NIST website and ran it against the model in order to verify that our model works as intended. So aside from the very easy to read pseudo-algorithmic representation, you can also simulate such a thing. Since it's C++, you can use any kind of C++ compiler to run the code. And we will now show how a property that starts here and goes down to here looks like. And specifically, we want to focus on the inner loop here. And what we use is completely normal C++ functions. So since we're also a software company, of course, we also wrote our G-test for that. You can run any kind of tests on these kinds of functions. And they're exactly how they specified in the NIST. So there's even testing on those specific functions. And what I mentioned earlier about the mode, so the property that we look at now here, that's related from the path that results from this else condition here. And we can see that this shows up directly in the property. So we have the condition that I is bigger than 16, because after 16 rounds, the algorithm changes a little bit, because they use these registers to do some backtracking. And after 16 rounds, the algorithm changes, and we execute this part of the code. And that's exactly expressed here in the assumption. So we see, okay, we want to be bigger than 16, but less than 80, because once we're bigger than 80, we're done. So we want to actually have exactly this execution path here, and then of course, everything on the bottom, and then we would go back up again. And what we see is that the tool now figures out all possible assignments of state registers from the class and registers. And for example, here we have like a shifting where we shift the values back once. So we see that W10 is assigned W11 and so on. But also we see that any kind of computation that we have specified here also shows up in the property. So once the property fails, you can just look at the counter example. All the relevant registers and wires and IOs will automatically be shown by the tool, and you can see what your design is doing wrong, where exactly. So it's very, very specific. Just some numbers for the end. It took us 2 weeks to implement the model. To be fair, the code writing was not the problem, but understanding how SHA actually works, making a C++ implementation that's equivalent to the SHA, that was what took most of the time. Then pushing the button on our tool, it took like a minute to generate the assertions. And then, as I mentioned earlier, we had to do the refinement on the primary IOs. That's just something that we have to do that took about like 30 minutes. And yeah, we generated 900 lines of code, just properties. The RTL is about the same size, and our C++ is only 300 lines of code. Simulating the test vectors that I mentioned took only 20 seconds, so it's quite fast if you need to do another regression because you got to fix something in the algorithm. But also, we get full convergence in less than 12 hours on a formal run. That depends a little bit on the tool and resources and the amount of licenses you have, but no matter if it's 12, 8, or 16 hours, it's still less than a day, which is fine for a complete formal verification of such a complex algorithm. And yeah, we're also working on getting rid of the last automatic step on the primary IOs. Since ChatGPT-4 is released, we now have a trained AI model that gives us with 80% accuracy already a refinement. So we also removed that effort. And that's the end of my talk. Thank you very much for attending. And yeah, if you have questions, feel free to ask.
Are there any? Just see if there's any unknowns. Any questions from the audience? Yeah. Is that hand going up?
Yeah. When you showed that generated assertion, which had like multiple and terms on the right-hand side of implication, do you actually decompose that into each term? Because if like every term on the, so if every term there could be 0, do you have to keep iterating around to find each term that could be 0?
Well, it's a formal proof, right? So,
but you could split all that up and just have.
Oh, you mean I have one property per assertion?
Yeah, you could have one property per answer.
That's what I was talking about earlier. So that we can do. So if the proof wouldn't converge, you would start like tell it to now split everything up, but you can do the math yourself, right? There's like a lot of assertions in here, so we probably end up, I don't know, having 500 properties.
Yeah, okay.
But that's not a problem if you have enough licenses, right?
Yeah, sure. Thank you.
More licenses is always the answer, I think. What the question is.
Yeah. Hi, you made it look very easy, but it's not always generating the property. There's a pseudocode that goes behind the property. So is your tool able to generate the pseudocode as well, or is it just the properties that are generated?
If you have a formalized spec, we can also generate you the pseudocode. But yeah, I guess that's the problem, right? So if you do not have that formalized spec in some way, it clearly defines what the design should do, yeah, then you have to write the pseudocode by yourself. So that's the trade-off you have to go through.
Okay, so I think we'll leave it there. And we've got coffee now for the next half an hour. And then we break up into 4, just to make it even more complicated. So in here, we've got the latest topics in verification, and we've got, there's a talk in here on the next generation process of verification. Is basically around RISC-V. There's a talk in here on applying AI/ML to verification as well, and then we have another talk from Doulos in the same room as last time. That was a bit of a squash last time. but hopefully that will be useful. And that's this time going to focus more on, I think this is the more on formal verification versus simulation. Then another VHDL verification track, and finally in the middle two rooms, that's 3 and 4, we've got UVM for AMS. Okay, so hopefully there's a track you'll find interesting for either back in here or one of the other 3. Okay, thank you.